Okay, everyone, I want to talk about a classic problem. I think I've seen it in every calculus book I've ever taught out of over 30 years. Like I said, it's a classic example. But before I do, I just want to do a little preliminary stuff that leads up to it. Review stuff, really. I'm assuming that you're all familiar with whatever vector fields, um, what it means for a vector field to be conservative. You're all familiar with line integrals of vector fields, the fundamental theorem of line. So I'm assuming a lot, okay, because I just want to lead up really to this one particular example. So, but let me remind you first the definition, right? I think we're all familiar with. A vector field F is conservative on a region if there exists a scalar function, we'll say phi, such that the vector field is the gradient of that function on that region, okay? So as an example, is the vector field F equals X and Y conservative? You may remember this is a radial field, okay, but is it conservative? In other words, can we find a function phi whose gradient is equal to xy? Well, let's see, we want this to be true. So give me a function whose partial derivative with respect to x is equal to x, and whose derivative with respect to y is equal to y. Yeah, okay. Yeah, that'll work. X squared over 2, right? You've done this before, right? You're thinking antiderivatives. Let's see. So let me check. The derivative of my function with respect to x is x, right? By the power rule. The derivative of it with respect to y, though, is not y, right? This would be 0. So we'll go back and amend it and add an extra term to it. Okay. And now we see that the gradient of this function is, in fact, equal to our vector field xy. So by our definition, it would appear that we found that the vector field is conservative. I will say yes. Okay. Well, what about this three-dimensional vector field? Okay, is it conservative? Well, let's see. We want the gradient of some function phi, some scalar, which by definition is this, to equal our vector field F. Give me a function phi whose derivative with respect to x is equal to z. What would that look like? Yeah, xz. Good. Notice also, everybody, that the derivative of this function with respect to z, the third component, is x, which we do have. However, the derivative with respect to y would equal 0, and we need it to be 1. So, all right, so we'll go back and amend it. We'll add a term to it. Okay? And so the gradient of this function phi is equal exactly to our vector field f. And so by our definition, yeah, the vector field is conservative. Okay? All right, now, another reminder, something that you've all done, the 2D test to determine if a vector field is conservative in the plane. All right, so let F be equal to Fg, and let that be a vector field defined on a connected and simply connected region R in the plane. Remember, simply connected basically it means no holes in it, okay? The components of the vector field have continuous first partial derivatives also defined on R. Then we say F is conservative on R if and only if these two partial derivatives are the same. I won't go into the proof. Again, I'm assuming you've all seen this before. Remember, we're leading up to that one classic example, all right? So as an example, determine whether the vector field given here is conservative on R2. Well, let's see. We'll call that part A. Can you give me a potential function for this, right? Usually that's what we call the function phi, whose gradient is equal to the vector field F. What is it? right? Remember now, I need a function whose derivative with respect to x is equal to e to the x cosine y. Think antiderivative now. Yeah, good. E to the x cosine y. Now, is the derivative of this with respect to y equal to the second component? Yes, good, it is, right? The derivative of e to the x cosine y with respect to y. In this case, e to the x would be the constant. The derivative of the cosine is negative sine y, and we have that here. Okay? So, yeah, it would appear our vector field is conservative on R2. And we found its potential function. Now, what should the value of the line integral be, assuming that C is any simple, closed, piecewise smooth, oriented curve in R2? What should that be? Right, right. It should be equal to 0, right? The fundamental theorem of line integrals, let me write this down, tells us so, right? Because for such a curve, the initial point and the terminal point would be the same. And the fundamental theorem says that you're allowed to evaluate a line integral of a conservative vector field by evaluating the potential function at both ends of the curve. And of course, if they're the same, then we would get 0 back. That's exactly what we would expect. Okay? All right, now, here's the classic example. All right? Let the vector field, and you probably have all seen this, right? Regardless of what calculus book you learned out of. Okay, let f be given as follows. Y over x squared plus y squared for the first component, negative x over x squared plus y squared. Show that the two partial derivatives in the 2D test are equivalent, and then show that the vector field is equal to the gradient of the inverse tangent function of x over y. Okay, so let's do that. Let me get a clean piece of paper. By the way, everybody, here's what the vector field actually looks like. Okay, notice it rotates around the origin. All right, well, let's see what we got. I will take the partial of f with respect to y, and I'll use the quotient rule to do it. Okay. Now, the derivative of the numerator is going to be 1 times the denominator, minus the top times the derivative of the bottom, which would be 2y, and that will simplify to x squared minus y squared over this denominator. Okay, so far so good. In a similar way, I will take the derivative of my second component, g of x and y, with respect to x. Use the quotient rule again. Now, the derivative of the numerator is negative 1 times the denominator. Okay, minus the numerator times the derivative of the denominator. Simplify. Minus minus is a positive. So again, we're going to get x squared minus y squared. And those two partial derivatives then are the same. So it would appear that our 2D test has been satisfied if you're just looking at the surface. Okay. Next. Show that the vector field is equal to the gradient of the inverse tangent of x over y. Okay, well, that's just straightforward calculation. Okay, so we'll take the derivative of this with respect to x. And then with respect to y. Okay. And then what I'll do for the first one, as I simplify everyone, what I'll do is I'll rewrite the fraction 1 divided by y is the same thing as y divided by y squared. Sorry about that. There we go. So I'll multiply 1 times y. Across the denominator, y squared times 1 is y squared plus y squared times x squared over y squared is x squared. And in a similar way, this second component, and this is exactly equal to the given vector field F. Okay? Now, part C of that classic example, okay, there it is right there. Evaluate the line integral where C is given by the unit circles for t between 0 and 2 pi. What do you expect the answer should be? Yeah, you would expect the answer to be 0, right? Well, let's find it. Yeah, let's actually calculate the line integral, and we'll use the brute force method for evaluating line integrals. In other words, we're going to put it in parametric form. Okay. Okay. So my line integral is going to be replaced with the integral from 0 to 2 pi. Okay, my vector field F is right here. Okay, so put it in parametric form. So replace all the x's with cosine t, all the y's with a sine t. Notice in a denominator, again, you're going to get sine squared plus cosine squared is equal to 1. So my first component is just going to be the sine of t. Second one is going to be negative cosine t. Dot that with the differential of r. Okay, well, that's going to be negative sine t dt, cosine t dt. Multiply the corresponding components. And that's the fundamental identity. You can factor out the -1 from that, right? You can have the fundamental identity. All of this then will be -1 over the interval rather from 0 to 2 pi will result in this. And that is not 0 like we might have expected. Okay, so question for us is what went wrong? What happened? Right, so that's part D. Given A and B, why is the solution to part C not 0? What happened? And is the vector field conservative or what? Well, for one thing, the 2D test actually doesn't apply. Right? If you look at back, gang, if you look back at the 2D test, right, we had, let me bring that back up. Right, here's our 2D test right here. Okay. But it says that the vector field and the components of, or the derivatives of its components have to be defined on a connected and simply connected region R in the plane, whereas components have continuous first partial derivatives on the region R. Notice that this vector field is not defined at the origin. And our circle right here, our circle C, encloses the origin. So there's that, right? The other thing is this. I'm going to make a note here. The domain of this vector field is R2 minus the origin, right? So if you think about it, all of R2 has a hole in it at the origin. So in this particular instance, we're talking about a region that is not simply connected. It's got a hole in it. Notice for this one right here, what about the inverse tangent function? What can you tell me about that? Right, the inverse tangent function. Gang, this function, its domain is R2 without the entire x-axis, right? Because for any point along the x-axis, y is equal to 0, and you're going to have division by 0 on the argument right here. But notice the domains are different, right? The domains are different. So these two functions, the vector field and the function phi, which in this case is inverse tangent, they are not defined on the same regions, okay? They are not defined on the same regions. You remember, here's an analogous situation, right? Remember the fundamental theorem of calculus from Calculus 1, right? The fundamental, here's a reminder. I'll just put it right here. Right, that's one part of it. But remember, what was the condition on f and the derivative of f? What was the condition on these? Right. They both had to be continuous at the same place, namely the closed interval from A to B. Right? Fundamental theorem says in order for it to apply, the function f and the derivative f prime, they both have to be continuous in the same area, the same location, the closed interval from A to B. So, and if they're not, then it doesn't apply. And you've got the same situation, an analogous situation right here. Why is that, right? Because you might be asking yourself, well, isn't the vector field conservative anyway? Because according to the definition, right here's the definition. Isn't it true that a vector field f is conservative on a region if there exists a scalar function phi such that f is equal to the gradient of that scalar function on that region? See, we have to be a little careful though, right? We've got to be careful. Domains are, right? We've been talking about domains, gosh, it seems like all the way back to algebra 2, right? You have to be careful, right? Different domains is the problem here. So is it true that the vector field f is equal to the gradient of the inverse tangent function x over y? Yeah, we showed it. Is the vector field conservative with that scalar function? No, it's not. Different domains. Now, we can fix this. Maybe what we do instead is say, let the vector field f equal this vector field for y greater than 0. Maybe, you know what I'm saying? So you want to amend the domain, so to speak, okay? If that's the case, right, then we can say that this thing, right, the inverse tangent of x over y, well, it will be defined for y greater than 0 because the x-axis is not included. So if we amend our domain where our function f is defined, in this case, we'll say in quadrants 1 and 2 without the x-axis, y is greater than 0. Then we say the vector field f will be conservative with the scalar function inverse tangent x over y because they both can be defined in that plane, y is greater than 0, or that half plane, excuse me, that half plane. Now, there's a number of ways I guess you could do that. This is just one way that you can do it, okay? But domains are important. Domains are important. And I think a lot of calculus books don't really, maybe they imply it in their definitions, or maybe they just don't do an adequate job. I'm not sure. But it's a classic example, and it tends to screw students up a little bit because once they see this right here, they think to themselves, well, wait a minute. Is the vector field conservative or not? It's equal to the gradient of a scalar function. So what's the story? And that's the story with this particular problem, different domains.